Hello and welcome. This is Xamarin University's XAM301 Mobile Application Architecture. In software engineering, a design pattern is a general, repeatable solution to a commonly occurring problem in software design. A design pattern isn't a finished design that can be transformed directly into code. It's a description or a template for how to solve a problem that can be used in many different situations. In this course, we're going to explore several common design patterns that we use when developing mobile applications. We'll see how these patterns work with the framework and APIs that are provided for each platform. So our goal today is not just to use these design patterns, but to understand when to use them and how they help us improve the quality and the maintainability of our code. Our first objective is to just talk about how to architect to maximize your code sharing. Presumably, one of the reasons you've adopted Xamarin as your mobile solution is because of the code sharing capabilities of the platform. A key aspect of sharing code across platforms is to keep the domain logic clear of the UI-specific paradigms and dependencies. This was formally described by Martin Fowler as separated presentation pattern, which is yet another application of the separation of concerns that we talk about with these patterns. Fowler applied separation of concerns specifically to the problem of building GUI applications, which are inherently harder to test because they require a user to drive them. He theorized that by separating the code that manages the presentation from the code that drives the behavior and the data, we could build more robust and automated testable applications. With presentation, we're referring to our app's visualization or user interface, and the domain is our data and our business logic, or all of the behind-the-scenes logic that drives our application. The problem is that without thinking about how they're related to one another, we often end up combining elements of both in our class relationships. That makes it more difficult to extend them and to test them independent from each other. So what we want to do is to keep these two aspects of our code, presentation and domain, separated from each other so that we clearly define the relationships between them and can independently test them and potentially even reuse them. To do that, we can use one of several known design patterns. There are a number of separated presentation patterns out there. Each takes a slightly different approach in how to separate the domain from the presentation of it. Model view controller, model view presenter, presentation model, passive view, supervising controller, model view, view model, and so many more. At first glance, they might actually even look the same, right? All of them have a similar structure. The visual difference here is the direction of the arrows that connect the pieces together. The goals of these patterns are the same. Separate UI-related code, your views, from logic-related code, presenters, controllers, view models, that sort of thing, from the data, models. This allows each of these to evolve independently. For example, you're able to change the look and feel of your application without affecting the logic or the data. So what is the difference between model view controller and model view presenter? Or why do we have two variations of model view presenter? These are the questions we're going to answer in this class. So by the end, you'll understand the similarities and the differences between these patterns, and more importantly, when it makes sense to apply one versus the other. Before we get into the details of the patterns, let's talk about the reason why you would want to choose one of them. First, they're well known, and they're used all over the place in one form or another. This means that there's a lot of consistency as you move from one app to another app using the same style. So improvements and components can often be shared between apps that are relying on one of these architectural styles. Another great reason, which I think is really the most important, is it provides a known structure to the app, making it easier to find things in the app, and for new developers to jump in and start, being productive. So for example, if you've ever seen an ASP.NET MVC application, it has an enforced defined structure to it. So if a new developer is assigned a bug, they might not know the business logic or domain, but they can quickly identify the route that gives them the controller, which points them at the view. That lets them quickly identify the code to look at versus having to poke through the code base trying to figure out, where the relevant classes are for that bug request. Following an architectural style can have a significant impact on your development lifecycle and may even reduce the cost and timeline to develop an application. And if you're developing multiple applications, standardizing on a style makes it easier when moving between projects. VB, Visual Basic, that was an amazing product that has had a bad reputation to a lot of professional programmers. VB was an amazing product that has had a bad reputation to a lot of professional programmers. Alan Cooper and his team revolutionized the programming world by making it accessible to a whole class of professionals and amateurs that didn't have to know about things like message pumps and pointers and memory management and software architecture. It simplified the process of building an application on Windows. And I'd argue that it contributed heavily to the adoption of Windows in businesses all over the world. You create a form, drag your controls onto it, double-click on them, and put the logic in the code behind. And that model has influenced every major IDE and GUI framework since, and it's still being used today by millions of programmers, from Windows forms to web apps. However, this approach also has a downside. That code put into the code behind is very closely coupled to the UI because it directly interacts with the controls on the screen. This approach is nice and straightforward, but only for really simple views. When the logic becomes more complex or the app gets too big, the code quickly becomes a maintenance nightmare. The root of the problem lies in the fact that building an app this way violates the single responsibility principle. And this principle states a class should have only a single reason for change. If a UI component has code for visualization, logic, and data, it has several reasons why it might have to be changed. For example, maybe you need to change the type of control that displays the data. And if that change also impacts the business logic, then you've violated this principle. This sort of problem is exactly what the separated presentation design patterns are all about. They are roadmaps on how to properly structure the application so that changes made to one layer of the application doesn't ripple through every aspect of the app. Applying this principle to your application has several key benefits. First, your code will be more maintainable. A change in UI, logic, or data will have less of an impact on the other areas of the application. This makes it easier to add new features with less cost in time and money. Second, your code will be more testable. The business logic and data of an application can be written in such a way that each component can be unit tested in isolation. UI-related code tends to be hard to test because it needs interaction to trigger the logic. Also, any visualization a lot of times needs to be judged by a human to see if it looks right. And finally, you can reuse and share your code. Mixing all your code together makes this very difficult because presentation code tends to be platform specific and inherently not shareable. Separating them out and enforcing strict relationships lets you replace the UI without completely having to rewrite all of the logic and data management. So let's look at some of these patterns in more detail. First, let's take a look at Model View Controller and how it applies to Xamarin iOS apps. Do you know any MVC platforms? You might already. There is the .NET MVC, ASP.NET MVC, Ruby on Rails uses MVC, and Xamarin iOS uses its own version of MVC. One of the very first separated presentation patterns was Model View Controller. Most likely you've heard of MVC and you've maybe used it in some form or another. This pattern was developed by a Norwegian computer scientist who spent a year at Xerox in 78-79. He developed the idea for MVC while working on Smalltalk. At that time, there really wasn't a notion of a GUI framework, if you think back. Instead, you had to draw the visual elements yourself in your code and managing the user interactions yourself as well. As a result, applications mixed the visualization code, the user interaction code, the logic, and the data all together. And he recognized that this approach limited some of the things he wanted to do. So he came up with a pattern to separate these functions into separate classes, each with a distinct responsibility. The link on the slide there has some great history on the genesis of this pattern. In its original form, built for Smalltalk, interactive views were split into two completely separate objects, the view and the controller. The view object performed display, but any click or interaction with the display was handled by the partner controller object. In Smalltalk, the view and the controller were simply the display and the action aspects of a single control on a screen. The controller didn't load, set up, or manage the view, and one controller didn't handle actions for more than one view. MVC has become a very common presentation pattern. It's applied to all sorts of application types from GUI to web. In fact, as you probably know, it's the default design approach for any iOS or Mac OS application, as Apple has adopted the pattern right into Cocoa and UIKit. That has led to a lot of misunderstanding of the pattern. In Smalltalk, the model was the central component of the object graph, with communication primarily occurring between the model and the view or controller directly. This implementation reflects how Smalltalk processed user input and how the framework was implemented. But today we have far more robust control models and GUI frameworks that do all the visualization and input delivery for us. So as a result, most modern frameworks that use MVC don't really apply it the way it was originally designed. And so we've changed the definition of the pattern. And because different platforms interpret it differently, you're going to find a wide variation in how it's implemented. So as an example, if you compare Apple's use of MVC in iOS with ASP.NET MVC, you might think that they are completely different patterns. So we're going to dive a bit deeper into the pattern and try to make it clear, while recognizing that there will be blog posts and even books that might spin these patterns slightly differently. Let's start with what everyone agrees on. MVC divides responsibility for the app between three distinct elements: the model, which is where our domain data is placed, the view, which presents the data to the user, and the controller, which provides the connection between the two. Notice in this diagram that the controller and the view both depend on the model. However, the model depends on neither the view nor the controller. This is one of the key benefits of separation. This allows the model to be built and tested independent of the visual presentation. The separation between the view and the controller is secondary in a lot of applications, and in fact, a lot of UI frameworks implement these two roles as one object. Now there's two major variations of this pattern. Which one you end up implementing is really dependent on how your models are changed. The first is the active model. This is where the model changes state without the controller's involvement. This can happen when other sources are changing the data and the changes have to be reflected in the views. Because the model is actively being changed independently of the other components in the system, the controller and the view need some way to stay synchronized to the model. We don't want the model to know about these other interested parties. If we couple them together, we end up with the same design we started with, where everything is all lumped together. So we loosely couple the model notifications using the observer pattern. This provides a way for objects to notify other objects about state changes without introducing dependencies on them. This is sometimes referred to as a publish-subscribe, and in .NET we can use delegates and events to implement this kind of loosely coupled notification. So here's how it works. When something changes the model, so for example, if your data is refreshed from a web service, it raises an event, or it sends a notification to a set of observers. So here you can see one of those observers would be the view displaying the model's data. The view would respond to this change notification by requesting the updated information from the model through a property getter or a method call. The view would then display the updated information. Alternatively, there are systems where the model is completely passive and it's always manipulated solely by the controller. So here there's no need for the model to notify other components about changing state because the changes are always well defined and known to the system. In this case, when the change occurs, it's the controller that is notified. It responds by changing the state of the model and then notifying the view that the data has changed. The view then retrieves the new state from the model and updates itself accordingly. Now that we've seen the big picture of MVC, let's look closer and look at the individual pieces. The model manages both the behavior and the data of the application domain and the logic to retrieve and persist that data. These can be singular objects like what you see here, or more complex object graphs made up of multiple objects representing our domain model. Often this is a domain model that can be based on a database or the results from a web service. In some cases, that domain model maps exactly to what the user sees, but in other cases it's formatted and altered and combined to be, presented visually. Models should always be platform agnostic and have no dependencies on how they're going to be displayed. So a good rule of thumb is to only use data which is part of the base .NET framework when crafting your model objects. If you have to take a dependency on a type from the UI layer, then you're mixing your layers. So here we have an employee definition with a set of data properties to describe that employee. The model exposes data to be presented by the view and responds to change requests, which are typically done by the controller. A view is a visual representation of one or more models, and it presents the information to the user and possibly allows the user to change that information. It's what the user sees and interacts with. It acts as a presentation filter in that it'll often highlight certain data values of the model and suppress others. The view should contain all the visual aspects of your application. That includes colors, fonts, layout, navigation paradigms. The view should not be responsible for storing data, although it can cache data for performance reasons or for state restoration. So for example, when our mobile apps are suspended. Since UI controls are platform specific, the view is not typically shared, and it'll be harder to test without actually running the application. Generally speaking, there really shouldn't be much to test in this layer anyway. It's strictly how the information is presented, and it has no knowledge of what the information is or what happens to it. A controller object acts as the intermediary between the application's view objects and its model objects. It's responsible for handling user input and then updating the model or the view. If the user interacts with the application by pressing a button on the keyboard or moving the mouse, the controller is notified of that action and decides what to do with it. It might respond by updating the model with new data or changing the view's state. In iOS, the controller is represented by a real type, view-controller, which is used to manage a single page in the application. iOS applications provide a derived implementation of this type in order to control a single screen of the mobile app. To receive notifications about UI changes, the controller will wire up event handlers or handle messages of some kind from the view. This is generally a deliberate thing the controller must subscribe to. so it decides the specific things it's interested in and listens for those activities. One critique of MVC is that because the controller is the intermediary between the view and the model, it often ends up being very large. In fact, a common nickname for this pattern is massive view controller. However, this is a misapplication of the pattern, resulting in a misunderstanding of the terms. The business logic belongs to the problem domain, and everything that is in the problem domain goes into the model in MVC. You should still use typical separation techniques within this layer, for example, classes and namespaces to organize the model. The controller should be solely responsible for passing the data from the model to the view and from the view back to the model. The controller is the bridge between what the user interacts with and how the program manages the state of the problem domain that it's intended to solve. Another way to put this is the controller can execute the business logic, but it should not contain the business logic. In Apple development for iOS and macOS, they utilize the MVC pattern to decouple the data and the view. Their implementation is a bit different than the defined pattern though. It's kind of a mixture of passive and active. In fact, it's really closer to another separation pattern referred to as supervising controller, but Apple calls it MVC. At the center of their implementation of the pattern is the controller. They call it a view controller, and there's an actual class type named UIViewController to manage it. Notice that all of the communication between the model and the view occur through the view controller, similar to how the passive model definition works. But the model does often support change notification in this world. However, only the view controller observes them. It then updates the view with the changed data. Again, unlike what we've seen in the formal pattern definition, the view's access to the data occurs through the interaction with the view controller. UIKit doesn't force this pattern on apps, but it strongly encourages it by all of the starting project templates. Loading from a storyboard almost always requires the use of UIViewController. Many views like UI search bar have corresponding controllers, UI search controller, to manage the state of the view. Classes like UI tab bar controller and UI navigation controller explicitly require instances of UIViewController to coordinate views as they're swapped in and out of the user presentation. Also, because each screen has a parent UIViewController that's responsible for all of the sub-views interactions, Apple's implementation tends to suffer from the massive controller problem because each UIViewController has to deal with not just the interaction but also with the setup and the configuration and the data display and updating and animations and layout of the child elements of its own view. This often bloats the view controller's class, making it a maintenance nightmare over time. There are many proposed solutions to this. At a minimum, in Xamarin, you can try separating these different responsibilities out through partial classes. However, the underlying cause is really difficult to solve because it's an artifact of how Apple has designed their GUI framework. So let's try this out in an exercise. In this first exercise, you'll be applying MVC in an iOS application. Pause the video, complete the exercise, and then we'll continue on. Now that you've seen MVC in iOS, let's look at the pros and cons of MVC. Some of the pros, as we saw, clean separation of roles in your app makes your architecture a lot more clear. It is well known, there are a lot of frameworks out there that implement it. Model classes and the domain is testable and reusable. And you can have multiple views of the same model. The cons, on the other hand, the view and the controller tend to be closely coupled, making independent changes a little bit more difficult. There is increased complexity, so it's not always suitable for smaller applications. And the controller can be that massive view controller. It can become a dumping ground of code because it tends to be the easiest place to put things. and it can be a little bit complex to understand and apply. Moving on to the next pattern, we're going to talk about applying Model View Presenter to a Xamarin Android app. MVC was created in a world where the program was responsible for completely managing all of the aspects of the GUI and interacting with the user. But the paradigm changed as more sophisticated systems were developed that took on a lot of the burden that originally was held in the app. The introduction of a formal UI controls pushed the visualization and user interaction responsibility into reusable components. A button knows what to do if you click it. A text box knows what to do if you type in it. This reduced the need for an explicit controller. However, there was still a need for separating out the logic of the application from the controls and the data, only at a higher abstraction level. This brought about a new related pattern called Model View Presenter. The Model View Presenter pattern describes a way to separate out the visual elements, the controls, from the logic, what happens when you interact with those controls, and the data, what data is displayed in the view. MVP is a separated presentation pattern where the GUI platform that we're using provides some of the controller aspects as part of the framework. So in this pattern, the view manages a lot of the visual behavior. For example, animations and selection. And then it notifies the presenter, which acts as a higher level coordinator between the view and the model. The presenter holds all the logic for the view and is responsible for synchronizing the model and the view. When the view notifies the presenter that the user has done something, clicked a button let's say, the presenter will then update the model and synchronize any changes between the model and the view. If the model changes independent of the presenter, it will implement some type of observer or notification pattern, and the presenter will then push those changes over to the view. Like MVC, there are a few variations to this pattern, depending on what you need and what the capabilities are of the underlying platform. But at a high level, they all function the same. You've probably seen some MVP frameworks, things such as Windows Forms, Xamarin Forms, and Xamarin Android. The first variation of this pattern is called passive view. In passive view, the presenter acts as a singular mediator between the view and the model. The view only has access to what the presenter provides, and any UI interaction that occurs is always pushed to the presenter for processing. The view is really just a visual layer implemented through the platform's UX framework. In this variant, the view is never directly aware of the changes in the model, and all view actions and data manipulations can be completely tested through the presenter, which is a key advantage of this approach. The downside is that the presenter tends to be larger because it has to encapsulate every change that occurs and push those changes to the view. To allow the presenter to be testable, we will typically use an abstraction to ensure that the presenter is framework independent. We don't want to rely on any UI control or feature because that would tie us to a specific platform, and that would make testing a lot more difficult. That means we decide on a contract up front that the view and the presenter will use to communicate, and all work is done through that abstraction. The actual contract would be an interface, or it could be a set of events. It just depends on how complex the interaction needs to be. So here's an example. Let's say we have an Android application with a login activity. Our view in this case is the activity. It creates and sets up the view for the app. Our presenter is a separate class where we will do the logic that's required for this page. Up front, we'll decide how these two classes will communicate, with the goal being that testing our presenter will allow us to fully test the view, and the presenter has no dependencies on the view for implementation. Our view class isn't going to care if the view is in an activity or a Windows Forms page or a Xamarin Forms page. The presenter just simply depends on the abstraction that we create. Here's one way to approach this. We can define a static class that contains two interfaces that will define the contract for our login page. The first interface, iView, is implemented by our activity, and it allows the presenter to set the email field or to clear the fields. Our second interface, iPresenter, is implemented by the presenter, and it has methods to invoke the presentation logic that we'll need for this page. Given that we aren't running tests on the view, our activity, this abstraction is optional. We could have a reference directly to the presenter without any harm. However, it's useful to provide an interface for both sides because it makes you think about how the two classes will relate to one another. The activity will have a reference to the presenter, or to the abstraction if we create one. Since the UI activity tends to be unsolicited, it will need to report those actions at specified times through callbacks. The presenter can have a reference to the view interface, but it's often not necessary unless the model can change without the view's involvement. In this case here, our model is driven by the presenter and the view, so we don't actually need a reference to the view in the presenter. This is why we've set it up so that the view is passed into the methods on the presenter contract. The second variation of the pattern is the supervising controller. In this style, the view interacts directly with the model without presenter intervention. This is often used when the underlying UI framework supports some kind of data binding infrastructure. So for example, Windows Forms or one of the XAML technologies. The presenter is still responsible for the presentation logic, and as it works, it changes the model data. However, it doesn't notify the view about the changes. Instead, the model is responsible for manipulating the state of the view directly. Most visual updates will take this path. However, this style doesn't prohibit the presenter from making view changes. For example, some logic might change the color of a view or cause the view to change in size or visibility, which might not be driven from the model. This approach tends to be less testable than the passive view. However, you generally end up with less code in the presenter because simple UI changes don't require the presenter to update the view. Notice that the same contract pattern is being used between the view and the presenter. That part of the pattern remains the same. As we saw with the MVC pattern, we want to be careful what we place into the presenter object. It should consist primarily of visual logic and handle the what to do logic. In the case of our login screen, the presenter's perform login would invoke some business logic in our domain model to actually authenticate the user and decide whether they have access to our service. The model would be updated based on that decision, and the presenter would move to a new activity to let the user into the app. The presenter doesn't make sense without a view. It comes with the view and it goes when the view is destroyed. It manages one view at a time. Some platforms have some lifetime oddities that we need to think about. So for example, on Android, when you rotate a device, the activity is destroyed and recreated. If the presenter is holding some state about the things happening in the view, we need to deal with this. However, we don't want to rely on Android services directly to store it. We want to be decoupled from the platform. So a better approach is to put some kind of cache into your model. It might even just be an in-memory cache or a dictionary service. The presenter dumps the relevant information that it cannot recreate here as it works. Then if the device is rotated, our activity is destroyed and the presenter goes away, and a new activity is created with a new presenter. It can reload the view state saved off from the original presenter working on this activity and lose no information. Alternatively, some people try to associate the same presenter with the activity. However, this approach can be kind of complicated and it may lead to lifetime issues with your objects. It's better to go for simplicity, and that means try to keep the relationship between the presenter and its view a one-to-one relationship. So let's try this out by applying MVP in an Android application. Go ahead and pause the video, complete the application, and we'll see you on the other side. Alright then, let's talk about the pros and cons of MVP. Some of the pros, of course, it can help us promote better architecture. Passive views allow for some high testability, but we have more code in the presenter. If we use supervising controller, we have more code simplicity, but our overall testability is a little bit decreased. Still highly testable though. On the con side, not all decisions are easy to make. Right? Should we persist the presenter? How does it align with the life cycle of our app? The app needs to create and connect presenters to views, and the model must provide some sort of change notification if it changes independent of the presenter. Next, let's talk about applying model view ViewModel to a Xamarin Forms app. So the final separation pattern we're going to look at is the model view ViewModel pattern, or MVVM. It's actually a specific implementation of a more loosely defined pattern called presentation model that was defined by Martin Fowler. The link to his description of this pattern is there on the slide. The primary difference between what Fowler described and what MVVM implements is the inclusion of a built-in data binding engine versus a more abstract observer pattern. MVVM has become particularly important in the XAML world, where we have a built-in data binding engine. But it's also become a popular pattern on some web frameworks. And there are binding engines for iOS and Android that are available in open source community. In this variation, we rely explicitly on a data binding engine to provide the data for the view, replacing the controller or presenter that's used in MVC or MVP patterns. It was created by John Grossman at Microsoft. He was an engineer on the Blend team that had some Smalltalk programmers that brought their MVC influences into the project. Models and views are the same as before, and the pattern is deliberately layered here. The view model knows about the model, and the view knows about the view model. But the view model should not know about the view, and the model should not depend on the view model. The view model is an intermediary between the model, the data, and the view, the presentation. You can think of it as the model for the view, or you could even think of it as the view for the model. Either way is appropriate. It's essentially a data structure that is built specifically for the view to present. The view model doesn't communicate directly with the view. Instead, it exposes bindable properties and methods called commands. The view can data bind those properties and commands to query information from the view model and call methods on the view model. It's also not required that the view knows about the view model. XAML's data binding is all done through reflection by name. So as long as the object you are binding to has the right name properties, it'll work. So let's walk through the implementation of this employee view model here on the screen. The class must be public. It holds a model object that has a one-to-one relationship in this case, although it may have access to other models or data if necessary. View models can be shared across views, really. Think about it. Think about wizard-style UIs. The iNotify property changed implementation is here. This is required for the data binding infrastructure to work. The name property is just a simple wrapper around the existing name property from the employee class. This is a very common thing in MVVM, and it's actually one of the criticisms. You end up duplicating property values between the model and the view model. And of course the properties must be public as well. So talking about that idea of wrapping the properties, in a pure pattern, the model should never be exposed to the view. It violates the encapsulation. But design patterns are not set in stone. If it's convenient to implement iNotify property changed on the model and expose it from the view model, then it's not illegal to do it. Just be aware that if the model definition is changed, then this could ripple through the UI versus being isolated to just the view model usage. The view model is designed to help the view display information. So as such, one of the things it can do is coerce or convert values for the UI to display. So for example, we could take currency or date values and properly translate them to a culture-aware value to be presented. In traditional Xamarin Forms applications, we would usually need a value converter on the binding to do this sort of coercion. But with the view model, that becomes unnecessary. In addition, we can convert non-bindable things to properties that the view can actually use. For example, here we provide a supervisor property, which returns a loaded view model of the supervisor based on the integer identifier. This would allow the view to display information about the supervisor beyond just the numeric identifier, maybe their name or their department. Again, this makes the job of binding this information to the UI super easy because we have a nice intermediary in the form of the view model. The view model can also provide access to related information beyond just the model. This is actually one of the best selling points of the view model. Because each binding is limited to a single source object, it gets a bit complex when we need to pull data from various places to display our information. And the view model makes this trivial because we can create bindable properties that navigate the code structures and pull the necessary data in for the view to display. Again, the job of the view model is to help the view display the data. And lastly, the view model provides a place for inconvenient code to be placed. This is code that doesn't belong in the view because it's not visual in nature. But it also doesn't belong in the data representation layer either. So for example, consider things like selection. It's a transitory state that won't typically be persisted. Now it's clearly view-centric, but it's not really part of the view directly. We can also provide easy access to calculations and validations or transformations of the model data for the view to present. Here, for example, we're providing a progress property, which would drive something visual to display activity related to the calculation being performed. When supplying the view models to the binding layer, we will often use the binding context property to bind to our main view model, which then provides access to collections and other child view models that can make up our system. This is one approach, but again, it's not part of the pattern. You can supply view models to bindings however it makes sense to your application. For example, you could have a static property that exposes a view model and then use the XStatic markup extension to provide it as the source property for a binding. View models are the bindable surface for your UI, and so as such we tend to create several of them in our application, one for each piece of data that's being displayed. In a pure MVVM system, we would wrap every model in a view model, but that's not really necessary in a lot of cases, particularly if the model data is read-only or already implements iNotify property changed. In these cases, you might have just a few view model representations that expose properties that are actually models. Often you'll have a master or a main view model, which provides access to all the others in your system. There's no enforced rule here. Do what makes sense for your application that you're building. But we want to take advantage of the fact that the binding system relies solely on the name of the property. So you could bind to models initially, and then if you find you need to do some coercion, maybe add some UI logic or extend the model in some view-centric sort of way, replace it with a view model in a later iteration. So our employee example showed a single employee model for a single employee view model. And that is often the way it will happen. You'll have a one-to-one relationship between a model and a view model, and a one-to-one relationship between the view and the view model. However, this is also not a rule. View models can be shared across views, and a single view model can have references to multiple models. It all depends on your application's needs. One of the view model's jobs is to present data to the view so that it can be visualized, but it shouldn't be dictating how that data is visualized. That's the view's job. Let's take a look at the code you see on the left. At first glance, it looks reasonable. We want our supervisor's name to be shown in a specific color. However, we're now enforcing certain view stylings from the view model. What happens if we decide we'd rather show a supervisor in a different color, or a different font, or bolded, or maybe we want to animate the text? Then we'd need to update both the view and the view model. Also, color, the type, is platform specific. So by exposing the color directly to our view model, it becomes a lot less shareable. The better approach is to provide a mechanism, often a property, that indicates if the employee is a supervisor. Then the view contains the visual logic to control the visualization. This means, updates in the visual only happen in the view. And the view model remains platform independent. So let's take a moment and have a lab on applying MVVM in a Xamarin Forms application. Once again, pause the video, complete the lab, and then we'll see you back on the other side. In this class, we've just scratched the surface of MVVM and Xamarin Forms. You saw the basics of the pattern in the lab. However, there are a lot of other patterns that are often used with MVVM, and some conventions that we've found work best to deal with these things like navigation and selection and UI alerts and view models. We can't cover all of that in this class, but we have a dedicated class that picks up from here and goes into all those details. If you plan to use MVVM or just want to learn more about how to apply it properly, make sure you register for XAM301 and go through that course. Now that we've tried out all three styles, let's contrast them. All three provide the same benefits, separating out our presentation from the domain. But they do it in slightly different ways, and all three can be applied to any of our mobile application platforms. That means that the choice of which one to use often falls on the developer or the developers starting the project. MVC tends to be used with iOS apps. MVP is valid for Android or Xamarin Forms, particularly simpler Forms projects where the complexity of MVVM just isn't necessary. And MVVM is primarily oriented around bindings, which makes it suitable for Xamarin Forms, although there are binding engines out there for Android and iOS. So we've had a chance to talk about architecting to maximize our code sharing, and we got to look at Model View Controller in iOS, Model View Presenter in Xamarin Android, and Model View ViewModel in a Xamarin Forms app. Thank you for watching our video on mobile application architecture. I hope to see you in a Xamarin University class.